All right, let's turn to the second important method for computing word similarity, distributional similarity. Now, thesauri have problems for computing similarity. We don't always have a thesaurus for a particular language, and even when we do, thesauri have problem with recall. So words are missing, phrases are missing, connections between senses may be missing, and in general, thesauri don't work as well for verbs or adjectives, which have less structured hyponymy relations. So for all these reasons, we often use distributional models of meaning, often called vector space models of meaning. And these tend to give you higher recall than hand-built thesauri, although they might have lower precision. The intuition of these distributional models of meaning comes from early linguistic work. So for example, Zelig-Harris in 1954 said oculist and eye doctor occur in almost the same environments. So if A and B have almost identical environments, we say they're synonyms. And Firth, back in 57, said, "You shall know a word by the company it keeps." So here's an example. We have a bunch of sentences about Tesguino. Nita says, a bottle of Tesguino is on the table. Everybody likes Tesguino. Tesguino makes you drunk. We make Tesguino out of corn. So from these context words, for a human, it's very easy to guess that Tesguino means some kind of alcoholic beverage, some kind of beer made out of corn. So the intuition for an algorithm is two words are similar if they're just surrounded by similar words. Very simple idea. Let's see how to make that work. Remember the term document matrix we saw in information retrieval. So each cell in the term document matrix was the count of a term T in a document D. So we called it the term frequency of T in D. And we thought about it, what meant to be a document was to be a count vector. So a column in this term document matrix. So the document, As You Like It, the Shakespeare play, is a count vector over lots of words. I've shown you just 4 words: battle, soldier, fool, clown. So As You Like It is a count vector. So two documents are similar if their vectors were similar. So Julius Caesar, high counts for battle and soldier, low counts for fool and clown. Similarly, Henry V, high counts for battle and soldier, low counts for fool and clown. So we saw that Julius Caesar and Henry V, if they were a query in a document or two documents, they were similar by this vector similarity method. And we're just going to use the same exact intuition for deciding if two words are similar. So look at the words in a term document matrix, and now a word is a count vector. And two words are similar if their vectors are similar. So fool has high counts in the document As You Like It and the document Twelfth Night, and low counts in Julius Caesar and Henry V. Clown has high counts in As You Like It and Twelfth Night, and low counts in Julius Caesar and Henry V. So we say that fool and clown are similar, but probably battle and fool are not similar because battle has high counts here and low counts here, but fool has the opposite. It has high counts here and low counts here. So the intuition of word similarity, distributional word similarity, is instead of using entire documents like we used for information retrieval, let's use smaller context. We could use a paragraph, or we could use just a window of 10 words. And now we define a word by a vector over these context counts for whatever this context is. So let's suppose we use context of 10 words to the left and 10 words to the right. Here's a sample example I've grabbed from the Brown corpus. So here's some words: the word apricot, the word pineapple, the word digital, and the word information. And I've shown you for each of them just one set of context: 10 words before apricot, 10 words after apricot, from one of the uses of apricot in one document in the corpus. And here's 10 words before and after pineapple, and so on. So from the various documents, examples I've grabbed from the Brown corpus, some examples for each of these words looking like these examples, I can compute little counts, and I can build myself the term context matrix. So here's the term context matrix for these 4 words: apricot, pineapple, digital, information. They don't ever appear with the word aardvark, but the words digital information have the word computer within the 10 words of them, twice for digital and once for information, or the word pinch occurs with apricot and pineapple, and the word sugar occurs with them, whereas the word data and the word result tends to occur with the word digital and the word information. Now again, we say two words are similar in meaning if their context vectors are similar. So apricot has a 1 for pinch and a 1 for sugar. Pineapple also has a 1 for pinch and a 1 for sugar and 0 for computer and data. So that tells us that probably these words are similar. Whereas digital and information, their counts occur in other words like computer, data, and result. So they're probably similar as well. Simple intuition, just like what we saw in information retrieval for comparing documents. But now we're comparing words and using a reduced context. Now for the term document matrix for information retrieval, we used TF-IDF weighting. We didn't use raw counts. We used various kinds of weighting, sometimes TF, sometimes IDF, sometimes both. Now for the term context matrix, it's very common to use a version of pointwise mutual information called positive pointwise mutual information. So let's look at that. Pointwise mutual information is an information theoretic method that says, do events X and Y occur more often than if they were independent? So the pointwise mutual information between two things X and Y is the probability of the two occurring together divided by the probability of the two, the product of the probability of the two independently, and we take the log of that. So you can see that if the two things occur more often than you would expect by chance, more often than you expect by independence, then the numerator will be much higher than the denominator. So between two words, the pointwise mutual information is the log of the probability of the two words occurring together times the product of the two words occurring independently. And positive PMI simply replaces all the negative values with 0. So imagine that we have a matrix F, our term context matrix, we'll call it F for frequency, and we've got words labeled by rows labeled by words, and we have columns labeled by contexts, which could be a context word. So we saw, for example, a context word aardvark or computer or data or pinch or so on. And we're going to take our here's our counts. In each of these counts is is f sub ij, the frequency of row I, column j. So we're going to turn those into probabilities first. So we'll say that the probability of a word I and j occurring together, the joint probability of a word I and a context j, is the frequency which they appear normalized by the sum of the frequency of all words in all contexts. So we sum over the entire matrix. That's the denominator n. The probability of a word, that's a row I star, is the count of all of the contexts that word occur in. So we sum over all possible contexts, and we sum all the counts for that word in those contexts, normalized by n. And the probability of a context is the sum over all words that a context occurs in, those counts, again, normalized. And we take these probabilities, the probability of a word and a context occurring together, times the probability of a word, over the probability of a word times the probability of a context. We take that log, and that's our PMI. And our positive PMI is if it's less than 0, we replace it with 0. So let's see how that works in practice. We've got our I made a simpler little matrix of counts here for working through our example. So the word digital occurs in the context computer twice, in the context data once, in the context result once, and never for pinch or sugar, okay, as we saw before. And again, our probability of the joint probability of a word and a context is the frequency with which the word occurs in the context normalized by the total n, the sum over of all counts for all words in all contexts. Let's first compute n. N is the sum of all these things, 2, 3, 4, 10, 11, 12, 13, 14, 15, 19. So n is 19. We've got 19. Our denominators are going to be 19 for all of our various probabilities. So now the probability, the joint probability of the word being information in the context data, so word is information in the context data, we've got our f sub ij is 6, and our n is 19, so we have 6/19 or 0.32. So that's the joint probability of information in data. Now we need to compute the probabilities of words and the probabilities of context. So the probability of word, we just sum a row over all contexts that word can occur in. So the word information occurs 11 times, once in this context, plus 6, plus 4. So we have a total of 11 times over, again, n of 19, or 0.58. So that's the probability of a word. And we do the same thing for contexts. We sum over all words that that context occurs with over those counts and normalize. So for the context data, we have a 1 plus a 6. So we have 7 over 19, or 0.37. So if we do this computation for all of our examples, we'll get this little matrix. Here we have the joint probabilities, all the joint probabilities. Here we have the marginals, the probability of the words, and the probability of the context. So again, here's our 0.37, and that's the probability of data, and here's our 0.58. That's the probability of the word information. And there's our 0.32. Good. So now we're ready to compute PMI. Recall that PMI is the log base 2 of the joint over the two marginals. So that's going to be our 0.32 divided by our 0.37 times 0.58. And then we'll take the log of that. So that's 0.58 or 0.57 using full precision. And we can see here that if we take this log, that we get positive numbers for computer being linked with digital, and information with data, and pineapple with sugar, and so on. And we've replaced any of the time we got negative numbers, since this is positive PMI, we've replaced the negative numbers with zeros. Now the problem with PMI is that it's weighted toward infrequent events. And there's a lovely survey paper by Turney and Pantel that walks through some of the ways that you can alleviate this. But it turns out that very simple methods like Laplace smoothing can actually help. Let's look at how this works with add 2 smoothing. So here I've just added 2 to all the counts. So we just have simple add 2 smoothing. And recomputed our probability table, again with our marginals for the context and the word. And now what I've shown you here is our positive PMI tables. Here's our original table for no smoothing. And here we are with add 2 smoothing. And what you'll notice is that in the original table, without smoothing, the link between apricot and pineapple and sugar is very high. We get a very high PMI, despite the fact, I don't know if you remember, that the counts were just 1. Whereas data for which we had a lot more evidence, counts of 6 and 4, the link between information and data or information and result, had much lower PMI values. Adding 2 affects the lower counts more than the higher counts, and we can see that the larger counts haven't changed very much, but we've discounted those excessively high PMI values, and now we have much more reasonable related numbers for our PMI. So that's the first half of our introduction to distributional similarity, and we'll turn in the second half to how to use cosine metrics to actually compute the similarity.